What's up, everybody? This is the multiple choice walkthrough for the test that's going to happen on Monday/Tuesday. All right, so without further ado, I have the formula sheet handy, ready to go. I have a calculator ready to go. Let's get into it. So here's our first question. All right. So, a survey was conducted at a movie theater to determine moviegoers' preferences for different types of popcorn. The results of the survey showed that brand A was preferred by 65%, with a margin of error with plus or minus 3%. What is meant by that margin of error, that plus or minus 3%? Does it mean that 3% of the population that was surveyed will change their minds? No. 3% of the time, the results of a survey are not accurate? No. 3% of the population was surveyed? No. The true proportion of the population who preferred brand A popcorn could be determined if 3% more of the population was surveyed. None of these are seeming right. It would be unlikely to get the observed sample proportion of 65% unless the actual percentage of people... Okay, that one's wordy, but it would be unlikely to get our p hat unless the actual percentage of people in the population was between 62 and 68%. That is correct. The idea, what we're talking about here, is that confidence intervals and the margin of error, whatever the population proportion is, we just don't know what the true proportion is. We don't know what that value is. But when we construct a confidence interval, what we're doing is this. We take a sample. The p hats that we get are going to follow this normal distribution. I just don't know which one of these p hats, is the 0.65 number. I don't know. Maybe 0.65 is like a little higher than the true mean, or maybe 0.65 is a little lower than the true mean. That would mean, so if I take a single p hat, maybe my confidence interval goes something like that, and it captures the true mean. Maybe my p hat is right here. Build a confidence interval around that. Yep, that also captured the true proportion. Every now and then, you're gonna get a p hat that's like way off in the tail, and when you build a confidence interval around there, you're going to miss the true proportion. But this event is not going to be unlikely. All right. Number 2. In an opinion poll, 25% of a random sample of 200 people said they strongly opposed to having a state lottery. The standard error of the sample is approximately... Okay, so the standard error, that's just a fancy way for saying the standard deviation of the statistic. We're talking about a proportion. So you can flip over into this handy-dandy formula sheet, and we can look for the standard error of what? Of a single proportion or of two proportions? It's only a single proportion. I only see one sample of size 200. So that means the formula, the standard error for our p hat should be the square root of p hat, 1 minus p hat, all over n. So p hat is 25%. 1 minus p hat is 0.75. And it was a sample of size 200. So throw all that into your calculator, and let's see, 0.25 times 0.75 over 200. 0306. So that means A is going to be our correct answer. All right. A survey was conducted to determine what percentage of college seniors would have chosen to attend a different college if they had known what they know now. In a random sample of 100 seniors, 34% said they would have attended a different college. A 90% confidence interval for the percentage. Oh, okay, so this one, I should just be able to throw this straight into my calculator. It's a 1 proportion z interval. So stats, tests, go on down until you get to 1 prop z interval. It's A on my calculator. And let's see, in a random sample of 100. So it's 34 out of my 100 seniors said that they would go somewhere different, and a 90% confidence interval. C level is 0.9. Calculate, and that's all there is to it. 262 to 0.418. So what your calculator is doing, just in case you wanted to know, your calculator is taking your p-hat, adding, subtracting some z-score times p-hat 1 minus p-hat all over n. So you could throw all that into your calculator yourself. You could start with 34%. The z-score for 90% is 1.645. You could do all this by hand if you wanted. I don't know what 1 minus 34 is. 0.34. 66 over 100. You could do all that by hand too, but it would still give you the same answer. Of course, you're going to want to use your calculator though. All right. A radio talk show with a large audience is interested in the proportion P of his listening area who thinks that the drinking age should be lowered to 18. To find this out, he poses the following question to his listeners. Do you think the drinking age should be lowered to 18 in light of the fact that 18-year-olds are eligible? This is kind of a biased question, but I don't know, maybe he's a biased kind of guy. He asked listeners to call in and vote. Of the 100 people who phoned in, 70 answered yes. Which of the following conditions has been violated? Are the data from an SRS or the population of interest? Well, the population of interest is what? Just his listeners? Or no, it's the population of interest is adults in his listening area, right? That's our population of interest. But this is definitely a voluntary response type of poll, right? He's like, in order to participate, you would have to be listening to the show, hear the question, and feel inspired to call in, right? So that's not a random sample. So this is definitely not, that one's definitely been violated. What about, is the population at least 10 times as large as the sample? The sample is 100 people. Is it reasonable that there's 1,000 adults in his listening area? I think that one's okay. You know, the population, if it's a large audience, right? So that's reasonable, I guess. We don't know for sure, but it's reasonable to assume. And then n is so large that both the counts of NP and failures and 1 minus p are 10 or more. Well, it tells us the count of successes. That is 70, right? Because 70 out of the 100 people said yes. And the count of failures, therefore, is the other 30 people said no. So are both of those numbers bigger than 10? That one's okay. So I think A must be it's the SRS condition that's violated. All right, number 5. Which of the following will reduce the width of a confidence interval? If you increase the confidence level, is that going to increase? Oh, this is reduce the width. Sorry, reduce the width. Okay, sorry, I'm looking for a better estimate. I want the confidence interval to get skinnier. All right, so increasing the confidence level, will that do it? Well, I don't think so, because if we have a confidence interval, say like, you've got some like 90% confidence interval, if I increase the confidence level, instead of capturing the middle of, say, 90% of the distribution, if I suddenly switch to capturing 95% of the confidence of the distribution, that's getting wider, right? So increasing the confidence increases the width. Okay, so not A. What about increasing the sample size? General rule of thumb, anytime you increase the sample size, everything gets better. So yeah, this is going to help. The reason why that sample size, we've talked about sampling distributions. We know that if you increase the size of the sample, that results in a skinnier distribution. So if you're trying to take 90% of this big, wide, fat guy, or 90% of this nice, skinny interval, higher sample sizes will be narrower. That will reduce the width. What about decreasing the standard deviation? That's also going to shrink how wide the distribution is, and with it, the confidence interval will shrink. So we're talking about 2 and 3. 2 and 3 only. There you go. So it's answer choice C. Moving right along. You want to Design a study to estimate the proportion of students on your campus who agree with a statement. Your student government is an effective organization for blah, 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 blah. All right, so you want a 95% confidence interval, and you want the margin of error to be 0.05 or less. The minimum sample size required is approximately... Okay, this is one of those solve for the sample size problems. You can either just dump those answer choices in there and see which one gives you an answer that's 0.05. Or I guess a little bit lower than 0.05 is what we're looking for. But don't be afraid of algebra. The margin of error is, we want the margin of error to be 0.05. Actually, technically, we want it to be less than 0.05. The formula for the margin of error, though, it's always some magic z value times the square root of p hat 1 minus p hat all over n. So I'm going to solve this equation for n. But wait, you need to have values for z and p hat in order to solve for n. So 0.05. The z value is okay. What's the, we want a 95% confidence interval. You might already have this value memorized, but just in case you don't, imagine trying to capture the middle 95% of every distribution. That would leave half of 5% in each tail. And if you grab your calculator, if you want to know what that value is, you can do inverse norm of whatever is in the tail. Apparently, that magic value is 1.96. 1.96, positive and negative 1.96. That's the boundaries that chop off the middle 95% of any normal distribution. Okay, so the magic value is 1.96. I also need an estimate for p hat, but there's a problem. I don't have an estimate for p hat. So what do I do there? Have we talked about this in class? I bet we have. If you have no prior information about the problem, then the magic p hat, the p hat that you use is going to be 0.5. Why? Because 0.5 maximize, by using 0.5 up here, 0.5 times 1 minus 0.5, that gives you the biggest possible numerator in this formula. If you pick any other decimal than 0.5, then you're going to end up with a smaller margin of error. And we want to guarantee that it's never going to be bigger than 0.05, so we want this numerator to be as big as possible. And the number that does that is 0.5. You can also think about it in terms of, like, if you have no idea what the true proportion is, like, what are you going to use for your p hat? Like, just, is there any reason to, like, argue that it should be closer to 1 or closer to 0? No, just split it right down the middle. You have to use some number, just split it down the middle. Okay, so now algebra. What value of n will solve that equation? I like to start with the answer. So there's my 0.05. I'm first going to divide off the 1.96. So divide by 1.96. I'm going to divide off that z-score. Caution, it's going to give you a very small decimal. The next thing I'm going to do, actually 0.0255, and there's some more digits there. The 0.0255, that is the square root of 0.5 times 0.5 over something. The next thing I'm going to do is get rid of the square root symbol. So with that tiny decimal that's already in my calculator, I'm now going to square it. And it's going to get even tinier. Sorry, my pencil is not working. Okay, so now I have 0.00065 something. I'm deliberately, I'm trying to keep all those decimals in my calculator's memory so that I don't have to worry about round off error creeping up on me. And so the final step would be to, what's the value of n? I like the algebra trick that says this number and this number can sort of switch places for free. So to figure out what n would have to be, we'll keep your 0.5 times 0.5 on top and divide by that tiny little decimal. There you go. The actual break-even point would be 384.16. But since I can't ask 0.16 of a person, how many people do you need to guarantee that it's going to be lower than 0.05? Yeah, so make it 385. Round it up to the next person. So answer choice C. I kind of circled D too, but you know what I'm talking about. All right, number 7. An opinion poll asks a random sample of adults whether they favor banning ownership of guns. A commentator believes that it's more than half of all adults. The null and alternative hypotheses would... Okay, so either it is 50%, it either is half, or this commentator believes that it's more than half. So the alternative hypothesis is going to be involving like greater... Is it equal to 0.5 or greater than 0.5? The problem is there's two that apparently might be correct. Is it A or is it D? It's D. Why isn't it A? You don't write your null and alternative hypotheses. You don't use statistics. Don't use HAT. Your null and alternative hypotheses are these big claims about how the world works. So there is no mystery about what the p-hat's going to be, right? Like, you want to say all adults. We think that it's more than half of all adults, not just more than half of the sample, right? So no hats. These are both nonsense null and alternative hypotheses. You never use hats. All right, number 8. A 95% confidence interval for the proportion of Canada beer drinkers who prefer Lion Red was found to be something to something. Which one is the following is correct? Does that mean that 95% of beer drinkers have between a 23 and a 28% chance of drinking Lion Red? No. There is a 95% probability. Okay, already, whenever anybody starts talking about like making probability statements, I know that whatever comes next is probably going to be wrong. There's a 95% probability that the sample proportion lies in the interval. No, because the true probability, like oh wait, hold on. The sample proportion. The sample proportion is always the sample proportion is always the center of the interval. So there's not a 95% probability. Like 100% of the time, the sample proportion is in the interval. That's ridiculous. But it hasn't stopped AP statistics students from saying stuff like this. All right, what about C? If a second sample was taken, there's a 95% chance that the confidence interval will contain 0.25. No, that means you're putting way too much emphasis on this one specific confidence interval, right? This is one of a million confidence intervals I could have constructed. There's a separate confidence interval for every single p-hat. So, there's no guarantee that anything would repeat. So nope. What about D? The confidence interval indicates we would likely reject the null hypothesis that p is equal to 0.25. No, 0.25 is in that interval, so we wouldn't be rejecting it. Our confidence interval is supporting that the proportion might indeed be 0.25, so that's not right. So it must be E. We are reasonably certain that the true proportion of beer drinkers who prefer Lion Red is between 24 and 28. Yep, that's good. Honestly, I think that's like a weaker time. Whenever somebody asks me to interpret a 95% confidence interval, I think I've said it before, but I really like making the statement. I like saying something like, if we repeatedly generated lots and lots of 95% confidence intervals, 95% of the intervals would capture the true proportion. So you want to try and say that you want to try and indicate that it's confidence not in this one specific interval. 95% confidence is confidence in the methodology. This is a method that works 95% of the time. If I was to make tons and tons and tons of confidence intervals, 95% of the confidence intervals would capture the true proportion and we'd miss 5% of the time. What about this one right up here? I don't know whether that's one of the ones that got it or one of the ones that missed. All I know is that over time, if I was to do this over and over and over, I'll be right 95% of the time. All right, number 9. In a large Midwestern university, the class of entering freshmen, we took an SRS of 100 freshmen in 2013, 20%. So 20 out of 100, 20% finished in the bottom of their class. Admission standards were tightened, so a couple years later, 10 out of 100 finished in the bottom third of their class. So is it getting any better? Is the proportion, well, they're saying let P1 and P2 equal the proportion. So is the proportion in 2013 equal to the proportion of students finishing in the bottom class? Has there been no movement over in that 5-year period, or has the proportion of students finishing in the bottom third of their class has it dropped? Right. I would want, ideally, if admission standards have tightened, the proportion should be lower 5 years later. So we're gonna, this is a 2-proportion test, right? We're comparing 2 different samples. So let's go into our calculator. Tests, let's do a 2-prop Z test. And let's see, this is saying that, so in the first group, it was 20 out of 100. And the second group, it's 10 out of 100. And we think that the proportion is, we think that it is greater, the first one's greater than the second one if the admission standards have tightened. So I mash calculate, and it turns out I get a test statistic of 1.98. The p-value is 0.02. So is that p-value, is that low enough to reject the null hypothesis? Well, it is at the 5% level. So, so this looks like the correct decision. Reject the null hypothesis at the 5% level. We can talk about why A is wrong. We are 95% confident the admission standards have been tightened. That doesn't sound quite right. And 95% confidence intervals are like 2-sided anyway. This is a 1-sided test. Obviously, B and C are opposites of each other. So C is not right. D, there was not significant evidence of a decrease in the proportion of freshmen that were admitted. There was a significant, and that's what we just showed, right? It's very unlikely. That 2% number, that p-value, of 0.02 tells me that there's less than a 2% chance that we would have seen these kind of numbers if the null hypothesis was true, right? So either we got just like stupidly unlucky, or maybe it was the null hypothesis that was wrong in the first place. That's the one. All right, and then E, if we reject the null hypothesis at the 5% level based on these results, a type 2 error may have occurred. Nah, I mean, rejecting the null hypothesis, that we could have resulted in a type 1 error. Type 2 errors are what might happen if you don't reject the null hypothesis. Remember that chart. All right, we're almost done. Number 10, in a test of p equaling 0.4 against p not equaling 0.4, a sample size of 100 produced a test statistic of 1.28. The p-value is approximately equal to, okay, so what are we doing? We're talking about, we have a normal distribution and we got a test statistic of 1.28. Our data, whatever they are, like this sample of size 100, the data ended up being 1.28 standard deviations above the mean. So the idea is like, what's the p-value? Well, the p-value is the probability of being there or worse. So what I need to do is I need to calculate the probability of being above 1.28 on the normal distribution. So that's not that bad. You just grab normal CDF and go from 1.28 to 1E99. All right, that's about 10%. Why isn't that the answer though? Because of this alternative hypothesis. Do you see that it's a two-tailed hypothesis test? This is saying we were testing to see whether it was bigger or smaller than 0.04. So if there's a 10% chance I'm off, then I'm that wrong in this direction, we could have also been wrong in that direction, right? So the total p-value is actually, includes the 10% up here and the symmetric 10% that's down there. So we're actually talking about 20%. Our p-value is 20.20. Double it because it's a two-tailed test. If it's a left or a right-tailed test, you don't have to worry about doubling it. But two-tailed tests, yeah, the area and we're counting the area in both tails. All right, An SRS of size 100 is taken from a population having 80% successes. An independent random sample of size 400 is taken from a population having 50% successes. The sampling distribution of the difference in sample proportions has what standard deviation? Okay, so what's the standard error for the difference in sample proportions? Formula sheet. This formula sheet says the standard deviation, well, we have a choice. The standard deviation, it's going to be one of these two bad boys. That's the standard deviation of the difference. Do we have any reason to believe that that the proportions are the same? Because if this was a hypothesis test situation, we would be assuming that the proportions are the same. We'd use this formula. But I don't think there's any reason to assume that those groups are the same, right? We don't have any reason to believe that, so I'm just going to use the normal formula. So that normal formula is it's p hat. So it's p hat and 1 minus p hat in the first group over the first sample size. Then it's p hat and 1 minus p hat in the second over the second sample size. Yeah, I'm just combining those two random variables. So my calculator, let's see. So it's the square root of 0.8 times 0.2 over 100 plus 0.5 times 0.5 over 400. Calculator says 0.047. Done. And number 12. Which of the following is true? A highly significant result indicates that the sample result never happened. No, it can still happen. It just might be weird. So that's not right. If the probability of sample data this is so wordy. If the probability of sample data yielding a statistic as or more extreme than a given value is approximately 0, then we have good indication that bias must have been involved with the data collection. Okay, first of all, it's word soup, but the probability of sample data yielding a statistic as or more extreme than a given value, y'all, that is just a wordy way of saying the p-value. What is the p-value? It's the probability of seeing our kind of results if the null hypothesis is true. So if that probability, if that p-value is close to 0, if it's really small, then what? Do we have good indication that bias must have been involved? No. If the p-value is close to 0, then do we have good indication that the value of the parameter could be significantly different than what's stated? Yeah, that's what the p-value means, right? If we get a really low probability, then what that's telling me is that maybe the parameter that we're testing in the null hypothesis, maybe it's wrong. So I'm already feeling C is probably going to be the answer, but let's check out D. If the p-value is approximately 0, then we have good indication that whoever stated the expected value is lying. Well, they might not be lying. No. Yeah, it's definitely, it's C. All right, and I believe that's all. Good luck on the test on Monday/Tuesday. Bye.